Let's graph this function without a calculator by applying the four main principles of a function and then filling in the rest from those clues. The first main principle or main object you want to calculate is the x-intercepts. The x-intercepts of a function in general are found by setting that function equal to 0 and solving for x. Well, if you look at this equation here in the lower right corner, you'll notice it says fraction equals 0. The only way that a fraction can equal 0 is if the top is 0. But now if you look at this equation, it says logarithm equals 0. The only way the logarithm can equal 0 is if the argument is 1. After all, the logarithm of 1 is 0. But the only way this argument could be 1, you'll notice, is if x were -4. There's no math procedure here. They're simply just looking at the function and saying, oh look, if x were -4, the argument would be 1, and the natural log of 1 is 0. Therefore, that's the solution to this equation, and therefore x equals -4 is my intercept. Well, now that I've found where the x-intercept is, I want to know the behavior near the intercept. So I'm going to plug in a number slightly to the left of 4, then I'm going to plug in a number slightly to the right of, I meant to say -4. Let's start on the left side of this number by plugging in -4.1. Plugging -4.1 for x gives us this. Well, we can't really calculate this accurately without a calculator, but we don't need to, because our goal is not to get a numerical value for this, but simply to determine whether the quantity is positive or negative, thus determining the behavior to the left of this intercept. Well, it turns out this quantity here is a positive number. How do I know that? Well, look at the fraction. The bottom is negative, but so is the top. Why is the natural log of 0.9 negative? Because the natural log of any number between 0 and 1 is negative. And since I have a negative divided by a negative here, and therefore a positive y value, watch the x-intercept, I now know that my graph is going to be above the x-axis to the left of that intercept. I'm not suggesting it's linear as shown in this picture, but simply that the graph has to be above the x-axis at that point. Now that I've analyzed the graph to the left of this intercept, let's plug in a number slightly to the right of -4. If you plug in, say, -3.9, you'll get this. Again, I'm not interested in calculating this to any degree of accuracy as much as I am just knowing if this quantity is positive or negative. Well, it turns out it's negative. Why is that? Well, because the natural log of 1.1 is a positive number. Why is that? The natural log of anything greater than 1 is a positive number. So I've got a fraction here, which is a positive divided by a negative. And as we know, that's a negative. Now what I just determined, that is slightly to the right of that intercept, I have a negative y value. Therefore, watch the intercept, the graph must be below the axis in that point. Again, I'm not suggesting the function is linear here. In fact, it isn't. What this picture is meant to represent is that the graph passes through this intercept in the fashion shown, with some curvature, of course, and not the false linearity shown here, but we get the general idea of the graph, and that's good enough. So that's the first of 4 key features of this graph. Let's go to the second key feature, which is the y-intercept. In general, y-intercepts are found by plugging in x equals 0, which I've done here. But this quantity doesn't exist. Why not? Because you can't divide by 0. And since that quantity doesn't exist, then there must not be a y-intercept to this function. Moving on to the third key feature, vertical asymptotes. Vertical asymptotes are generally created by two mathematical situations. Look at the top of your screen and notice that there's an x in the denominator. One of the situations that creates a vertical asymptote is a denominator of 0. Therefore, if x were 0, I would have a 0 denominator, and thus, in most cases, a vertical asymptote. So I have one of my vertical asymptotes at x equals 0, and I'll draw that now. But a denominator of 0 is not the only algebra situation that might create a vertical asymptote. The other one is the logarithm of 0, and we also have a logarithm in this problem. So if the argument is 0, in other words, if x plus 5 were 0, i.e. if x were negative 5, then we would have a 0 argument to our logarithm, and therefore, in all likelihood, a vertical asymptote. So negative 5 is my other vertical asymptote in this problem. I'll draw that now. But simply finding the vertical asymptotes isn't necessarily enough information. I like to get the behavior on either side nearby these asymptotes. So let's go through the 4 calculations it's going to require to analyze the behavior on either side of these asymptotes. I'll start with the vertical asymptote of negative 5 and plug in a number slightly to the left of that, say negative 5.1. Now that I've plugged negative 5.1 into the function, I would like to calculate this, find out if the quantity is positive or negative to know how the graph is approaching the asymptote. But this quantity doesn't exist, because if you look at the logarithm argument, it works out to negative 0.1. And the logarithm of a negative number isn't real. And since it's not real, it's not graphable in a real coordinate plane. And therefore, there is no behavior to the left of that first asymptote. In fact, in more general terms, look at the top of your screen at the equation. You should be convinced that any x value below negative 5 will create a negative argument, therefore a non-real output or an ungraphable output. So not only is there no behavior slightly to the left of this asymptote, this function isn't real if you go to the left of that asymptote at all. So we shouldn't consider anything to the left of negative 5 at all, however close to this asymptote. Now let's consider something slightly to the right of negative 5, say negative 4.9. If x is negative 4.9, let's work out this quantity. I've worked out the logarithm argument. Now, I'm not interested in knowing whether or not this quantity, or what this quantity is numerically. I simply need to know if it's positive or negative. Well, look at the numerator, the natural log of 0.1. That's a negative number. I don't need a calculator to know that, because the natural log of any number between 0 and 1 is negative. Hence, I have a fraction here, which is a negative, divided by a negative, which is a positive. So what does all this mean? It means when x is negative 4.9, I have a positive y value. Watch the graph and see that that represents that the graph must approach the vertical asymptote in an upward fashion on the right side of that asymptote. Now that I've analyzed the behavior on either side of negative 5, let's go to our next vertical asymptote, which is x equals 0. aka the y-axis, and let's analyze to the left and right of that as well. Let's start to the left side of that asymptote by plugging in negative 0.1. This will give us a good sense of how the graph is approaching the asymptote on the left side of it. Well, if you work this out, we've got a fraction. And once again, we're not expecting to know the value of this fraction. We simply need to know whether it's a positive or negative quantity. Well, if you look at the numerator, it's positive, the numerator anyways, because the natural log of anything greater than 1 is positive. So I've got a fraction here that's a positive divided by a negative. That, of course, is a negative. So what does that tell me? Well, I plugged in something slightly to the left of 0, and I got a negative quantity. Watch the graph. That means my graph is approaching that asymptote on that side in a downward fashion. And finally, in regard to vertical asymptotes anyways, let's look slightly to the right of 0 by plugging in positive 0.1. That works out to this, and once again, I don't need to know its numerical value, simply whether it's a positive or negative quantity. But for reasons previously discussed, this fraction is a positive divided by a positive, and therefore a positive. So what does all that mean? It means I plugged in 0.1 or something slightly to the right of that asymptote, and I got a positive y value. That means the graph is approaching the asymptote in that direction. And we're not done yet. That only completes the first 3 out of our 4 key features of this graph. The fourth key feature, of course, is the left and right end behavior. Well, as we've discussed earlier, there is no left end behavior. Suppose we tried to plug in negative 1,000 to get the left end behavior, or get a sense of it anyways. So this gives us a logarithm of a negative number, which doesn't exist in a real sense, and therefore it's not graphable. And as we mentioned earlier, there is no graph here to the left of negative 5. So no left end behavior to speak of. Let's move on to the right end behavior. To get a sense of the right end behavior, I'm going to plug in positive 1,000 for x. And remember, there's nothing special about the number 1,000. Other than the fact that it gives us a good sense of what happens to this function as x is getting bigger and bigger and bigger, i.e. as x approaches infinity. Now, if you look at this fraction here, we've got the natural log of 1,005 over 1,000. The natural log, or all logarithms really, are so incredibly slow growing that I would estimate the natural log of 1,005 might be 6 or 7 or 8. And while I wouldn't expect a student to know that, I do expect students to know that the natural log is a very slow growing function, so that the natural log of 1,000 would be way less than 1,000. So what have I got here? I've got a number way less than 1,000 in my numerator, which really is about 7 or 8, divided by 1,000. Now, 7 divided by 1,000, let's say, is a pretty small number. But imagine what would happen if x got even bigger, suppose 1,000,000. Well, I would have the natural log of 1,000,000 over 1,000,000, roughly. The natural log of 1,000,000 is a very relatively small number. It's about 15, I want to say. And again, I don't expect you to know that, but I do expect you to know that the natural log of 1,000,000 is a very small number compared to 1,000,000. And if we were to divide that by 1,000,000, we would get an even smaller number. And if you look at the very top of the screen, if you didn't get the concept of the end behavior there, then let me summarize it this way. Looking at the top of your screen, as x gets bigger and bigger and bigger, both the numerator and the denominator are growing, but the denominator is growing so much faster because of the slow growth of the natural logarithm inhibiting the numerator, that as x gets bigger and bigger and bigger, this quantity is going to be getting a much bigger denominator than it has numerator, and therefore will be approaching 0. And that's graphically represented by the graph approaching the x-axis here. Again, because of the slow growth of the natural logarithm, the bigger x gets, the bigger the denominator gets relative to the numerator, and hence the smaller this fraction becomes as we go further and further to the right. And that completes the 4 key features of the graph. At this point, you could simply connect everything up and be done and say that the graph looks like this. And on an exam, that would be fine. But it looks weird to me, partly because I don't like, these sort of jagged, awkward turns, but also because one of the things you'll learn in calculus is that graphs don't have these sort of sharp corners in them in most cases. So even though this is the totally acceptable answer in this pre-calculus class, I will show you a more scaled drawing of what this looks like. And that completes this problem.